Yeah, thanks for the introduction. This is joint work with David Woodruff. And I guess as always with Theory Lunch, if you have any questions, just interrupt and ask. We're eating our virtual pizza, so I probably okay, so let's get started. So this title is quite a mouthful, and I guess we should probably start breaking this up into a few terms. Okay, sorry, 1 second. So to understand the two main terms in the title, we first need to talk about the streaming model, which is something that we've all seen. So just a reminder, in
Samson,
the
can I pause you
streaming,
just for one? Sorry about this, but like your mic has
yeah.
the property that like I think unless you're like talking really directly to it, it completely cuts out.
Oh, really? Okay.
Yeah, so maybe if you can just make sure that you're pointed towards the mic.
Okay.
Thanks.
Okay. Yeah. Sorry. Thanks for letting me know. Okay. Yeah. So in this model, we have elements of an underlying data set S, and they arrive sequentially. So they arrive one in time, and the goal is to use sublinear space in the size M of the input S to evaluate or approximate some given function. Okay, so just as a vanilla example, let's suppose we have a sequence of bits, ones and zeros, and we want to count the number of ones. So we see these bits one at a time. At the end of the stream, we just want to output, in this case, 5. Okay, so this is pretty standard stuff. And it's clear that we can do this in just size log n space here. So what are problems that are frequently considered in this model? One problem is the problem of heavy hitters, where we're given a set of elements, and they all arrive from some universe which we'll associate with 1 through n. In this case, the stream induces a frequency vector f, and we'll let fi be the frequency of element I, which is how often it appears. For example, let's suppose we have the stream at the bottom of the screen. The stream will induce the frequency vector 5, 3, 1, 0 because there are 5 instances of the element 1, 3 instances of the element 2, and so forth. Okay, so that's the frequency vector. And now we define the L2 norm to be the sum of the squared coordinates of the frequency vector. Take that and then take the square root of that. So that will be the L2 norm of the frequency vector. And the goal is to find all elements I such that Fi is larger than epsilon times L2. And we don't want to report any elements j such that Fj is less than epsilon over 16 times L2. So basically we have some threshold epsilon, and we want to find all elements that are, kind of bigger than epsilon L2 in frequency. But, just defining this would be too easy. We could just report every single element. So we also have the demand that we don't report any elements that have threshold that are too low. So this is useful in DDoS prevention. Maybe you're on some network and you see traffic in this network and you want to deny any spam bots from being available on this network. It's also used in iceberg queries. So you have some database, you have queries on this database that are used frequently, and you want to find these queries so that you can store these information explicitly. Okay, so the heavy hitters problem utilizes this quantity L2, which is related to this frequency moments problem. So here we still have the frequency vector f, with fi being the frequency of element I. And we define fp to be the frequency moment of the vector, which is just the sum of the pth powers of the coordinates. And here, again, we're given an accuracy parameter epsilon. The goal is to output a 1 plus epsilon approximation to fp. And for example, for p equals 2, this is used often in least squares regression, and it's also useful for entropy estimation. Also, we kind of need it for our heavy hitters problem in the previous slide. Another problem that's frequently studied in the streaming model is the distinct elements problem, in which case we still have this frequency vector, and f0 is defined as the number of coordinates that are non-zero, and we want to count f0 up to a 1 approximation. So again, this is used in traffic monitoring to estimate the number of distinct users on a traffic network. So what's known about these problems? Well, there's really a lot of work on these problems, but the main takeaway message from all of these works is that the dependency should be roughly 1 over epsilon squared in terms of either the threshold parameter epsilon for heavy hitters or the accuracy parameter epsilon for counting the number of distinct elements or the FP moment estimation problem. Okay, so we can finally talk about one of the models in the title of the talk. So the first model we'll talk about is the adversarially robust streaming model. And in this case, we'll have elements of an underlying data set S, but they arrive sequentially and adversarially. Namely, we have an adversary and an honest user. So the adversary is on the left here, and the honest user is on the right. So the adversary will make some input to the honest user. They will see the output of the honest user, and then they will adjust their inputs by creating another set of inputs that ultimately induce this data set S with the goal that they want to mess up the honest user. So in this case, suppose we have a number of bits again, and the honest user wants to output the number of ones. So far, the adversary has not succeeded in fooling the honest party, but suppose at some point later, the number of ones in this stream is 2, but the honest party has output 3, and the adversary has succeeded. So another way to think about this is that you want to be correct on the stream at all times, but the input of the stream is not oblivious to the outputs at the previous stages. And this is pretty natural in applications. You know, for example, if you are querying a database, it's realistic to expect future queries on this database to depend on previous queries. There's also been a line of active work in adversarial ML. For example, we've all heard the works where we have a classifier, and perhaps by changing a single pixel in an image, we can fool a classifier completely by forcing it to output something else. So we certainly don't claim to do anything like that. You know, we don't solve those problems at all, but at least there's some motivation from those problems. So recently, there was some work by Ben, Elliott et al. Raj and David are also on this paper, and they gave algorithms for these problems that are well studied in the string model that are also robust to any adversary. So the main takeaway of the results in this paper is that they give a general framework that loses nothing in n in only a small 1 over epsilon factor. I guess the question then is what's just an epsilon between friends, since the previous paper just loses a 1 over epsilon factor? Well, if we see that there are, maybe 300 billion emails sent per day, if we want accuracy 0.01, so that 1 over epsilon is roughly 100, then taking log of 300 billion is like maybe 40. So actually 1 over epsilon is bigger than log n. So in some sense, we should care about the log n factors less than we care about the 1 over epsilon factors. I'm not saying that we shouldn't care about the log n factors, but we should definitely care about the 1 over epsilon factors. So this probably motivated some work by Hasidim et al. Recently. And they gave a nice paper that showed relationships between differential privacy and the streaming model. They essentially used differential privacy to hide the internal randomness of algorithms. And the main takeaway of their message is that 1 over epsilon losses are not necessary. So they get these space bounds in terms of 1 over epsilon to 2.5, although they do lose some log n factors due to the differential privacy methods that they use. But they show that 1 over epsilon losses are not necessary. So in this work, we show that actually no losses are necessary in terms of the tilde O notation. So we get both 1 over epsilon squared and tight dependencies on the higher order powers of n for each of these algorithms. Okay, so in summary, we kind of get the best of both worlds. We don't lose any log n, we don't lose any any factors of n, but we do get tight bounds on 1 over epsilon. And as I alluded to earlier, this is kind of the best known results, even for the vanilla streaming model, where we don't get an adversary. Okay, so the other model that we talked about in the title was
sorry, I have a question. So when you say the vanilla streaming model, could you just briefly describe how that model differs from the one you're using?
Oh yeah, sure. So I guess the best way to think about it is that the input of the vanilla streaming model is oblivious to the outputs at the previous stage. So you have some input. It could be adversarially designed in the sense that maybe the adversary knows your algorithm and it wants to fool your algorithm if it doesn't ever get to see any previous outputs, but it doesn't get to see, like I said, it doesn't see the previous output, so maybe it doesn't learn anything about the internal randomness of the algorithm.
Okay, and so that matters because we're allowed to fail some small fraction of the time. So the point is the adversary can't craft an input that would make us fail too often.
Yeah. In fact, I guess in a few slides later, I'll give an example of something that works in, I guess, the classic streaming model that doesn't quite work in the adversarially robust model. So hopefully that'll make it more clear.
Okay, thanks.
Yeah. But first, I'll talk about this other model, the sliding window model, in which the goal again is to approximate or evaluate some given function. And we want to use space sublinear in the size of the input. But here, only the m most recent updates form the underlying dataset S. Suppose we have a window of size 8, and we see these bits again in the stream. So we see ones and zeros until we see 8 bits. Everything that we see so far is going to be the underlying data set. But once we see the 9th bit, then the first bit implicitly expires. And until the stream ends, the data set is just going to be the most recent 8 bits. Okay, so at the end of the stream, we've seen a total of 11 bits, but we only care about the most recent 8 bits in the stream. And this can be challenging because the bits expire implicitly in the sense that we know that the 3rd bit has expired when we see the last bit of the stream, but we don't know the identity of the 3rd value of the 3rd bit. So the sliding window model emphasizes recent interactions, and thus it's a bit more appropriate for time-sensitive settings. So there have been algorithms that give a 1 over epsilon squared bound for a lot of these problems in the sliding window model. But for a lot of other problems, it's not known how to get 1 over epsilon squared. So Braverman and Ostrovsky in 2007 gave a general framework for a lot of sliding window algorithms, assuming that we have a streaming algorithm for these problems. And their framework loses nothing in n, but loses 1 over epsilon factors. In some cases, for frequency moments with p large, they lose a significant number of 1 over epsilon factors over the 1 over epsilon squared guaranteed in the streaming model. So we show that we can actually get 1 over epsilon squared algorithms for the sliding window model, and surprisingly, our results use the same technique as the adversarially robust model. So we do show that 1 over epsilon's factors are not necessary. Sorry, 1 over epsilon overhead factors are not necessary. Okay, so that's kind of the background of the talk. I guess in the next part, I'll first introduce an example of why the robust model is different from the vanilla model, kind of related to Isaac's question. And then at the end, I'll talk about these different estimators that kind of form the main theoretical contribution of our work. But I guess first I'll stop for any questions on the background that we've discussed so far. So a classic algorithm that's used in the stream model is due to Alain, Mathias, and Cecchetti, called the AMS algorithm. And the goal here is to approximate the F2 moment, which is the sum of the squares of the coordinates in the underlying frequency vector, up to 1 plus epsilon. So their algorithm is really simple. There's a good chance you've already seen it in a standard algorithms class, but let me just go over it again. So the frequency vector has length n, and we first generate a sign vector of length n. So S is going to be a sign vector. All of its entries are plus or minus 1. And we generate each coordinate uniformly at random and independently. So as the stream proceeds, we keep track of this value z, which is the dot product of S with the frequency vector. So this can be tracked in a stream. Each time we get an update to coordinate I, then we can update z by taking the corresponding sign and multiplying it by the, and then adding 1 or -1 based on the sign. Okay, so z is just going to be the inner product, S1, F1, plus all the way to Sn, Fn. And let's consider z squared. Well, by expanding z squared, we can see from linear expectation that it's just the sum of the expected values of Si, Sj, Fi, Fj. So I and j are coordinates from n. And when I or j are not equal, the signs are independent, so the expectation is just 0. So the cross terms are just going to contribute 0 to this sum. But when I equals j, Si is equal to Sj, and Fi is equal to Fj, so then the total expectation of z squared is just the sum of the squared coordinates, which is exactly what we want. It's F2 of the stream. By a similar calculation, we can see that the variance of z squared is less than roughly some constant times the F2 squared. So by taking the mean of roughly one over epsilon squared inner products, we get a 1 plus epsilon approximation to F2 by a standard mean variance argument using like Chebyshev's inequality. Okay, so the algorithm is really simple. We just keep track of 1 over epsilon squared of these inner products. We take the mean, and that's the entire algorithm. Okay, but this doesn't necessarily work on in the adversarial robust streaming model, because we can learn whether Si equals Sj from querying this algorithm on a frequency vector that has value Ei plus Ej. So we can query all the sums of the elementary vectors. And then if we let f, at the end of the stream, we define a frequency vector such that Fi is equal to 1 if Si is equal to 1 and -1 otherwise. So now we deterministically have z being m. Similarly, we have z squared equals m squared. So we certainly won't get an F2, we won't get a 1 plus epsilon approximation to F2. Like z, the expectation of z is m, and that's not going to be equal to F2. So what happened here is that we chose the frequency vector so that the signs of the frequency vector are exactly correlated with the signs of the sign vector that was supposed to be hidden in this internal randomness by the algorithm. So in a nutshell, the randomness of the algorithm is no longer independent of the input. And this is exactly why it fails for adversarially robust models. More generally, Hart and Woodruff showed that a similar attack works on linear sketches by iteratively learning the kernel of the sketch matrix and then choosing your input at the end of the stream to be something that's roughly close to the kernel. So you're going to output 0, but whatever function you want to evaluate will not be 0. So they show that linear sketches are not robust to adversarial attacks, and you essentially have to use linear space.
Just to make sure I understand something. So like in this attack, like the thing that the streaming algorithm outputs is actually the correct inner product of the plus or minus 1 vector with the frequency moments, right? It's just it no longer is necessarily close to the thing that it was trying to be a proxy for, the L2 norm.
Yeah, so outputs m, which is like the F1 of the stream. that which is not necessarily, you know, well, it's probably not going to be the F2 unless you've chosen your
Yeah.
at a certain location.
Okay.
Yeah, so the algorithm is correct for a certain thing, but it's not the thing that you want. Okay. So that's an attack that fools the AMS sketch. But the key from this attack is that deletions are needed to efficiently perform this attack. Namely, if we confine or we restrict this stream to have polynomial length, you know, not exponential length, just kind of short, then we can't actually do this attack in the in a short amount of time. And this is because we want, in the previous slides, we want to query the algorithm on all these values ei plus ej. So deletions are kind of needed because once we've queried E1 plus E2, to query E1 plus E3, we kind of had to delete the updates to coordinate 2 that we previously added. So the key is that deletions are needed to perform this attack, and similar lower bounds are known for the sliding window model in the sense that if you allow deletions in the sliding window model, a lot of algorithms do require linear space. And since we already have algorithms that work in sublinear space, we know that we should be assuming insertion only updates. So how did the previous algorithms work? So I'll first talk about the framework by Braverman and Ostrovsky. And the idea is that there's a property of functions called smooth. And a smooth function in a nutshell is that if B is a good approximation to A, then B union C will always be a good approximation to A union C. In other words, if you have some suffix B that is a good approximation to A, then no matter what input you see afterwards, the suffix B union C will be a good approximation to A union C. So given this smooth property of functions, there's a framework by Braverman and Ostrovsky that converts a streaming algorithm into a sliding window algorithm. And the idea is that they maintain a number of algorithms, and each time there are 3 instances that are kind of close, we delete the middle one. Then we use different checkpoints to sandwich the sliding window at the end. So if you got all that, that's great for you, but I think it will probably be more clear with an example. So let's consider the same example that we had previously. We have bits 0 to 1, or 0 and 1, and we want to count the number of ones. But let's actually be a little more loose and suppose that we just want to approximate the number of ones in the sliding window within a factor of 2. So we see these bits one at a time. We see 1 bit, and we immediately start a new instance of our algorithm. So here in this example, the stream will move from left to right. So when we see another bit, we start another instance of the algorithm. And you'll notice that the red instance and the pink instances do not output anything within a factor of 2, so we just continue. Now, after seeing 3 bits, the red algorithm has seen 2 ones, and the green algorithm has seen 1 1, which is the same as the pink algorithm. And now we have 3 algorithms that are within a factor of 2. Since we want a 2 approximation, we know that it's going to be safe to remove the pink algorithm because we can always query the red or green algorithms and they'll give an answer that's within a factor of 2 within the pink. Okay, so we continue this reasoning by adding on algorithms at each point in time, and then doing this maintenance procedure whenever we have 3 algorithms that are within a factor of 2. And at the end of the stream, we've seen 11 bits again. The sliding window contains the 8 most recent bits, which may not correspond with the starting location of one of the algorithms that we've maintained. But if we've done our job correctly, we'll have 2 algorithms that sandwich the start of the sliding window, namely in this case, the red and the yellow algorithms, and they'll be within a factor of 2. So we can actually ask either of these algorithms and they'll be within a factor of 2 of the number of bits in the sliding window. So in this case, the number of bits is 5, but we'll notice that 5 is at least 4, which is the number reported by the yellow instance, and at most 7, which is the number of ones seen by the red instance. Moreover, it's within a factor of 2. Okay, so 4 is going to be a good approximation. So that was the smooth histogram framework for the sliding window model. And now we'll talk about robust algorithms. And we'll see that they actually have a similar idea. So suppose we're trying to approximate some given function, and suppose that this function is monotonic and the stream is insertion only. Again, suppose that we have a streaming algorithm for this function. In the Ben Elliott et al. Paper show a framework that's called sketch switching. And the idea is, again, to start many instances of the streaming algorithm. But we do this at the beginning now instead of at each point in time. Now, we'll use an instance of the algorithm and we'll freeze the output. This is to prevent the adversary from messing up any outputs that's already seen. So each time the next instance has a value that's roughly within 1 plus epsilon more than the frozen output, then we'll switch to the next instance and freeze that output. Again, that probably wasn't too clear, so let's look at an example. So again, let's suppose that we want to approximate the number of ones that we see in the stream within a factor of 2. Rather than having new instances at each point in time, we'll start all of our algorithms at the beginning. So we have 4 instances of our algorithm that counts the number of ones. We're going to freeze one of these inputs. So suppose we freeze the red output. By that, I mean that the output of the red algorithm will never change no matter what happens when we see more. So at this point, we've seen 3 updates to the stream. The number of bits is 2. The red algorithm is frozen, which is what we've been outputting the whole time. And now the yellow algorithm, and actually most of the other algorithms, are not within a factor. Well, they're within the ratio of the outputs of these quantities to the red algorithm is going to be 2. So we know that if we keep listening to the red algorithm, we're not going to be within a 2 approximation. So what we'll do is that we'll switch to the yellow algorithm, we'll freeze its output, and we're going to keep reporting the value that's outputted by the yellow. So we continue to see, we listen to the yellow algorithm, we see more entries in the stream, and at some point, the yellow algorithm will no longer be accurate within a factor of 2. And at this point, we'll switch to the sketch that has not been used yet, and we'll just keep continuing in the stream. So again, at the end of the stream, we'll know that the algorithm we listen to will be within a factor of 2 of the total number of bits seen, because if it weren't, then we have switched to another algorithm that's still live and going. Moreover, the adversary can't mess up the output by any of these algorithms, because when an adversary finally sees the output of one of these algorithms, it's going to be frozen and not used again.
I didn't 100% get it. Is there any chance you're going to mention like how it works on the AMS algorithm?
Yeah, so I guess a quick rundown of that would just be that we have multiple instances of the AMS algorithm. So suppose we want to have a 2 approximation.
So this is just like having more plus or minus 1 vectors, right?
Kind of. It's more like, so we do have, it's more like more means in the sense that we take one AMS algorithm and it's the mean of 1 over epsilon squared sign vectors. And we view that as one algorithm. And now we run like log n algorithms in parallel. So we do have more sign vectors, but more importantly, we listen to like each group of 1 over epsilon squared sign vectors for a while. Then when we know that it's no longer accurate, we switch to another group of 1 over epsilon squared sign vectors. Does that make sense?
So it's like when the one group of sign vectors, the mean it gives is not approximately equal to the answers given by all the other groups?
Yeah, or just the next group. Just the next group. Yeah, you kind of like associate each group of 1 over epsilon squared with maybe an ordering of the stream in terms of like maybe this algorithm will output first, then the next one, and so forth. So if we take the condition that all of these algorithms are correct, then one algorithm will stop when it's no longer within a factor of 2 within the next algorithm.
I see. Will
So
this have like a
suppose,
lot at the beginning though? Because like, after you only see like one element like this. Oh, well. Okay, never mind. Sorry.
yeah, so the idea is that we'll switch to a different sketch each time the output changes by a factor of 1 plus epsilon. So we'll need roughly 1 over epsilon times log n extra copies. Assuming that the stream is polynomially bounded, then yeah, we just need like a log n extra number of copies. Because
Okay.
the value will double each time we switch. Yeah, so like Ryan alluded to, the key point in both the smooth histogram framework for the sliding window algorithms and the sketch switching framework for robust algorithms is that we kind of pay an extra copy, like an extra copy of this AMS each time the algorithm increases by 1 plus epsilon. So we'll use roughly 1 over epsilon squared space because that's the space used by a classic algorithm. It's in the classic streaming model. But we'll need to do this roughly 1 over epsilon times log n times. So the function will increase by 1 plus epsilon, roughly 1 over epsilon times, and this is where we get the 1 over epsilon cubed dependency for the robust model. And similarly, for the smooth histogram, we use 1 over epsilon squared space for each time the FP increases by 1 plus epsilon, but due to technical reasons for the smoothest parameter, we actually might need more than 1 over epsilon copies. We might need 1 over epsilon to the p copies. So I guess this begs the question, do we really need to pay 1 over epsilon squared space each time the function increases by 1 plus epsilon? So imagine some scenario where we're between 2 points in time where the algorithm has changed by a factor of 2. So we're just bumping along, and the algorithm has only changed by 1 plus epsilon. And we have a good approximation of the algorithm at the previous point in time. So suppose here that we have a red algorithm that is looking at the input of the frequency vector u. And this yellow algorithm has input frequency vector u plus v. And here v is kind of the suffix of the stream. So we see a number of additional, so the yellow algorithm sees a number of additional updates to the stream. And these updates are denoted by the frequency vector v. So if you want the frequency moment of u plus v, and I promise you that it's only within a 1 plus epsilon factor of the frequency moment of u, then all I'm telling you is just that the difference between these two quantities is just epsilon times the value on u. So now, since we want a constant factor approximation to this difference, I claim that we only need a constant factor approximation to So we want a constant factor approximation to epsilon times fp of u. So we only need a constant factor approximation to the difference. So this motivates a technique that we call sketch stitching that we introduce. And the point is that we can decompose the value of the function on the frequency vector u plus v into this difference, which is the first term in this parentheses. It's the function evaluated on u plus v minus the function on u. And then we add the value of the function on the prefix of the stream. So we telescope this term on the left-hand side into onto two terms on the right. And the first term represents the suffix of the stream, and the second term represents the prefix. And so we demand that we're within a 1 plus epsilon approximation for the prefix. So we need accuracy 1 plus epsilon here, which is pretty fine. But for the suffix, if this suffix is small, if this suffix is roughly epsilon times the prefix, then we only need a constant factor here. So we can afford a coarser approximation to the suffix. And this can decompose more generally so that instead of considering two frequency vectors, we can look at B frequency vectors. So we can have V1 and V2. And we can again decompose this function into multiple terms. So previously, we just had two terms in the telescoping sum, but now we'll have maybe V terms in the telescoping sum. And this looks intimidating, but you'll notice that the second term in each parentheses cancels out with the first term in the next parentheses. So all that's left is just going to be this first term. And if we define, the vector v to be the sum of each of the components, then this term is just u plus v, which is just the left-hand side. So this is pretty simple. But I haven't really told you why we need to decompose the frequency vector v into all these different terms. So this is the idea that we call granularity change, where we set each difference to be exponentially decreasing. So again, we've decomposed the function into a number of differences. And we haven't defined how these frequency vectors v1, v2, all the way to vb are denoted in the stream. So we're going to define them implicitly by saying that these are the vectors such that each of these differences in the summation are exponentially decreasing. Namely, we have that the last term is going to be roughly 1 over 2 to the b times the prefix. Okay, so previously we had an example where the frequency vectors v1 and v2 kind of split up the tail of the stream evenly. But now we're demanding that v2 is going to be much smaller than v1. And if we have more frequency vectors, v3 will be even smaller than v2 and so forth. So what this affords us is that we can have coarser and coarser approximations to each of these vectors vi. Okay. So in summary, we have these differences, and we demand that each of these differences are exponentially decreasing, which means that we just need 2 to the b epsilon approximation to the difference. And the hope is to use space roughly 1 over, well, to use less and less space because we need coarser and coarser. Namely, if we looked at this AMS sketch we had earlier, a 2 to the b epsilon approximation just uses space 1 over 2 to the 2b epsilon squared, which is much less than 1 over epsilon squared. So in summary, we have this framework. We have a number of algorithms running simultaneously for each granularity. We want to use smaller space for the granularities corresponding to smaller contributions. But we do need a multiple number of instances for each granularity because it can appear multiple times. But the idea is that the total space should be a geometric sequence, a geometric series, which sums to roughly 1 over epsilon squared. So all this relies on us actually being able to accurately approximate the difference. And that requires this concept called difference estimators that I'll talk about in the next. I guess this is also a good time to stop and ask if there are anything, any questions for the framework that we just gave. Okay, so moving on. Basically, I've given a framework that says if we have a difference estimator, we want to partition the stream into different points in time and run this estimator on these various frequency vectors that are kind of contributing smaller and smaller amounts, exponentially smaller amounts. So now the question is, how can we do this difference estimator and what properties do we want? So we say that if the difference is equal to 2 to the b times epsilon, does there exist an algorithm that approximates the difference with space roughly 1 over 2 to the 2b epsilon squared?
Is that supposed to be 2 to the negative b in the difference? Because right now it seems like it's a very large difference.
Yes, you're right. It's epsilon over, wait, sorry.
Maybe I'm not understanding.
No, I think this is fine. Because if the difference is larger, then we require a finer accuracy, so we need more space. Oh, sorry, no, sorry. I think yeah, you're right. You're right. It should be 2 to the 2b, or 2 to the negative b in the first term.
Okay, thanks.
But instead of looking at this 2 to the b times epsilon, let's actually parameterize this, so it's easy to deal with. So let's say that the difference is equal to gamma times the prefix, and we want to output the estimate within an additive approximation epsilon times the prefix. So f is generally nonlinear, but we can still do this in the sense that let's suppose we get a 1 plus epsilon approximation to each of the terms in the difference. So that's fine. Like looking at the fourth bullet point here, 1 plus epsilon approximations to each of the terms in the difference can actually give a multiplicative 1 plus epsilon approximation to the difference, which gives an additive epsilon approximation. So it gives what we want, but it uses space 1 over epsilon squared. And this is going to be true no matter what gamma is. So the point is that no matter what the difference is, you still use space 1 over epsilon squared. So this is not what we want, because as the difference gets smaller, we want to be using less and less space. So that doesn't quite work. We can also take constant factor approximations to each of the difference, or to each of the terms, but this can give a horrible approximation, right? Like it could actually give a negative amount to the difference if our constants are bad enough. Maybe if we look at a 2 approximation, maybe we output like this, the first term over 2, and the second term times 2, and then we end up with a negative value. So this is bad. We can't do a constant factor approximation to each of the terms in the difference. So our results are that we actually do have a difference estimator that uses space proportional to both epsilon and inversely proportional to gamma and inversely proportional to epsilon. So the point is that as the difference is smaller, we use less and less space. Okay, so let's talk about this for F2. So this is our F2 difference estimator, and it's going to be closely related to the AMS sketch that we mentioned at the beginning of the talk. Okay, so just as a reminder, for a difference estimator, we have that the difference is going to be parameterized by gamma times the prefix, which is just gamma times the function evaluated on u. And we want to output an additive approximation to the difference with error epsilon times the function evaluated on u, the prefix. So we can expand this left-hand side, and we see that it's going to be 2 times the inner product plus the inner product of v with itself squared. Now we have something that's known as an inner product property in the sense that 1 plus epsilon approximations to both the 2 norm of u and v gives an epsilon 2 norm u times 2 norm v additive approximation to the dot product u and v. So if we demand that the difference is at most gamma times the prefix, that means this term on the second line is at most gamma times the difference, right? Like all we're doing is just taking this equality and moving this term to the left-hand side. So we know that this sum is going to be equal to gamma times the prefix, which certainly implies that each of these terms is going to be less than gamma times the prefix. So we know that gamma times the prefix is going to be greater than the inner product of v with itself, and that this implies, using the inner product property, that 2 times the inner product is going to be less than not only the function evaluated on u, but actually something much smaller, 2 times root gamma. So we should think of root gamma here as like maybe epsilon or epsilon squared. If we think of this as epsilon, then we're saying that the first term in the summation is at most 2 times root epsilon times the prefix, which means that we only need a root epsilon approximation. So maybe this is a bit confusing, but the point is that if the the dot product is at most root gamma times the prefix, then to get an additive epsilon approximation, we just need a multiplicative epsilon over root gamma approximation. So again, think of gamma as epsilon. So we only need a root gamma multiplicative approximation rather than we only need a root epsilon multiplicative approximation rather than epsilon approximation. And recall from our AMS sketch that if we want a epsilon approximation, that requires 1 over epsilon squared space. So now we get our savings. Instead of needing an epsilon approximation that gives 1 over epsilon squared space, we just need root epsilon approximation that gives roughly 1 over epsilon space. And all we're doing is just using the AMS sketch. We're just maintaining 1 over 1 plus epsilon over root gamma approximations, which just means that we just keep gamma over epsilon squared rows of these sign vectors. So in a nutshell, our difference estimator for F2 is only keeping gamma over epsilon squared of these sign vectors, and we're just taking the mean at the end. That's our whole algorithm. Okay, so that's our F2 difference estimator. And now we have similar difference estimators for FP. The generalization for these sign vectors is typically what's known as a p-stable random variable, or vectors with entries that are drawn from this p-stable distribution. And that's how a lot of previous work study FP moment estimation on streams in the classic streaming model. But this requires a median estimator, and it's not clear how to analyze the median of a few differences. So it's not clear how the median of differences relates to the difference of medians. So instead, we use what's known as Lee's geometric mean algorithm, which is actually another way to compute the FP moment of a stream. So this algorithm is also pretty simple to understand. The analysis is involved, but all the algorithm does is just take the geometric mean of 3 inner products, and each of these inner products has entries that are drawn from this p-stable distribution. So you generate your inner vector, you take the dot product of that with your frequency vector, that gives 3 quantities. Take the geometric mean of these 3 quantities, that gives some value. And now you take the average of 1 over epsilon squared, the mean, the arithmetic mean of 1 over epsilon squared of these geometric means. And that will give you a 1 plus epsilon approximation to the pth moment on the frequency vector. So that doesn't give your difference estimator, but we can again decompose this this difference. Namely, we can decompose what's computed by the algorithm, and we see that each summon actually has this term that's roughly a sign vector dotted with this vector v. And this v is the suffix vector, which is much smaller. So all this is implying is that this variance for the algorithm is going to be much smaller than what we expect, and so we can use a smaller number of copies, which is basically the same argument we use for the AMS sketch. So again, the expectation is correct. The variance is much smaller than we expect, so we just need to run a much smaller number of copies and take the mean. And that's the entire FP difference estimator. So there are some generalizations of this for p bigger than 2. It looks like I'm running a little short on time, so I won't talk about this. But the main problem is that the variance could be much larger, so we need to do some other pre-processing to reduce the variance. And we do this by removing a number of heavy hitters. Finally, there are some tricks we use to remove additional log-n factors. The algorithm I told you right now has optimal 1 over epsilon squared dependency, but not optimal factors, not optimal dependency in n. So we use some known tricks to reduce. And I've kind of also just given you a framework for the robust algorithm. So I want to quickly wave my hands a bit and show how this approach also relates to the sliding window algorithm. So the top illustration is the intuition for the robust algorithm. We have a green algorithm that is accurate, and now we want to add suffixes to this green algorithm that are shrinking in magnitude. So we add these suffixes that are red, and they're kind of getting smaller and smaller. So this is the top picture. The red vectors are getting smaller, and we need coarser and coarser accuracy, accuracy 2 epsilon, 4 epsilon, and so forth to each of these vectors because their contributions are smaller. But the point is, we're adding these difference estimators as suffixes to the stream. For the sliding window model, maybe our active window is denoted by this square or this rectangle. And we have a green algorithm that encompasses this rectangle, and we want to subtract contributions of the stream from this green algorithm. So in the bottom picture, the largest green algorithm is what we have. The second green algorithm is already included within the window, and all we want to do is remove a number of prefixes from the stream. So again, we take these difference estimators and subtract them from the output of the green algorithm. Okay, so this kind of gives a forward and backward view of the stream and how difference estimators can be used for both frameworks. So in summary, we give a new framework for streaming algorithms. We use an idea called sketch stitching, which is combining multiple difference estimators using this telescoping sum that we had. And the other idea that we contribute to this framework is the granularity change, which is saying that we should define our vectors to be exponentially smaller in contribution. And since they're exponentially smaller, we can afford to use less and less space, and we give algorithms that we call difference estimators to do this. And that's our whole, that's our entire work in a nutshell. Okay, so finally, I want to do some shameless advertising. So Nesh, Raj, and I are going to be organizing a workshop on algorithms for large data. It'll be entirely online, and we'll be focusing on streaming, sketching, linear algebra, property testing, and learning, distribution learning. So yeah, this will be entirely online. Everyone's invited, and we hope to see you there. Okay, and I guess that's the end. So I'll open up to any questions that you might have. Thanks.
Hey, I guess I'm wondering, sort of zooming out from the specific idea of the difference estimator, like I'm trying to get a sense of what made it. It seems like the randomness of the algorithm is only affecting like there's only like short range dependencies on the randomness versus the output, and that's sort of a big part of what gives it good properties.
Yeah, exactly. That's you're absolutely right. Like that's absolutely crucial. So I guess the first observation is that a deterministic algorithm will be robust. Like there's no internal randomness there. So if we have a deterministic algorithm, then it's always going to be correct. And now we can view a randomized algorithm that's frozen as a deterministic algorithm. Like once a randomized algorithm is frozen, then it's always going to output the same thing. But the actual value of the stream is going to be growing. So the frozen output will be accurate up to a point, and at some point later, it will not be accurate, and actually it's no longer going to be accurate after that. But yeah, so the short-term dependency is due to this view of a randomized algorithm essentially being a deterministic algorithm because it's frozen, and also because before its output is revealed, nothing about its internal state is given to the algorithm. Like the algorithm only sees frozen outputs of other algorithms. So the internal randomness of this next algorithm is going to be independent of anything that the adversary can change in the input.
Okay, and sort of the big insight of this work is that it's sort of like the later algorithms can use earlier algorithms as input, not just do it all themselves afresh.
Yeah. Actually, I would kind of say that's mainly an observation of Raj's previous paper, the Ben
Okay.
Elliott et al. Work. They noticed that later instances are independent of previous instances. But here we kind of use previous instances to guide us in the sense that as we see more inputs, we still use what we've known to be correct from the previous input. But then we use coarser and coarser accuracies to like new updates. So if I see a new instance, if I have just switched algorithms, I have a new deterministic algorithm and I just revealed its output, it's probably going to be correct for a while because it was just correct, 1 second ago.
Right, and the
And the
function
moment can't
changes
change for a while.
slowly.
Yeah. So it's probably gonna be correct for a while. But we do want to be a bit careful. So we do want to keep track of a small number of updates in the future and kind of adjust the output accordingly. And I think that would be an accurate depiction of our main contribution or our main insight.
All right, thanks.
Yeah, thanks for the question.